So let's recall what we did yesterday. We were talking about algebraic theories, which is a bunch of math with some vague promise that it's going to turn into computer science eventually. And so I spoke about sort of a series of notions. So we started by saying, well, first you have a signature, which is just a description of the operations that we're going to use. So there are some operation symbols, and each one has an arity, which tells you how many arguments it takes. And out of these, you can build terms. And the way you build terms, it's always you build terms given some variables xi to xn. You can build a term, and the term is either a variable or it's an operation applied to the correct number of subterms, depending. So it has to be, you have to respect the arities. And you build these deductively. And then you can write down equations between terms. And then a theory is a signature together with some equations. So that was just the form, what is the form of an algebraic theory. And then we spoke about models. And before we speak about models, we explained what an interpretation was. And so the way that you give an interpretation, you give a carrier set. And then you have to explain for each of the operation symbols which map on the carrier set it's supposed to be. And then a model is an interpretation which satisfies the equations. And then I spoke about free models. And they're special. And then we started talking about trees, how to generate free models. So there was a universal property, and there were trees. And I'm not going to review that now, because we're going to go through it again at a slightly more general level. So what I'm going to start with now is I'm going to generalize what we were doing so far, because we have to generalize it in order to get what we want. So I'll do it on the other board, on the other side. And what happens is there will be two pieces of generalization. These arities here, so an operation, it takes a natural number. This is a natural number. So an operation can take 0 arguments or 1 argument or 2 or 3, but that's not good enough for us. We want an arbitrary amount of arguments. That's what we will need. So we need to generalize signatures, and we need to do another thing, which is parametrized operations. So we need to allow operations that have extra parameters. So let me do each one of them. Actually, let's see. I don't think I can fit it there. I'll just do it here. So the first thing is, so I have some random numbering system. I think I'm at number 4. What do you think? Okay, I'll be at number 4. Yes?
Start on the middle board.
Where?
You raise that board and start in the middle on the board.
I should raise this one.
Yes.
Okay, while I'm doing that, I'll try to figure out why, but okay. And when you see a little light bulb on top of my head, that's when I got it. Okay, so let's discuss first the general arities. Okay, so when you have an operation, operation symbol, and it has some arity ni, how do you interpret it? Well, when you interpret it in a model, it's going to be here a product of ni factors, right? So because this operation wants ni arguments, so we need to give it ni arguments. Now, there will be operations where this is not good enough, and so we need to generalize. And here, you could sort of make a mistake. If I ask, how do we generalize to arbitrary amount of arguments, then you'd probably think, oh, we have to allow infinitely many as well, because we've covered finitely many, so we want infinitely many. That's true, but how do you generalize to infinitely many? What will I use here instead of a natural number? Ordinal numbers, cardinal numbers, something like that. That's going in the other direction, away from computer science. That's a bad idea if you're going to use cardinal numbers, because that's infinite number set theory. Wrong way to go. So let's do it slightly differently. So there's a way to write this, right? So another way to write this is like this. Yes? But if I define n to be a set with n elements, concretely let it be the set of the first n natural numbers, then let me just do this in general, not just for I. If I have an n-fold product like that, okay, then that is going to be isomorphic to x to the n, where by this, when I say b to the a, that's just the set of all functions. This is set of all functions from a to b. And in fact, I'm going to use this and this notation as synonymous. So whichever fits my purpose, I might write it like this, or I might write it like that. This is simply the set of all functions from a to b. And if you're a functional programmer, you're saying, yeah, it's a function type, of course. But we're doing sets at the moment, okay? So is it clear that these two are going to be isomorphic? N tuples is the same thing as functions from an n-element set, because, well, you know, you just, the ith component is wherever you map I. So these two are going to be isomorphic. So we're really talking about how to generalize this exponent. What are we going to use for this exponent if I say it has to be arbitrary? And the answer is, well, arbitrary, anything. Why does it have to be a cardinal number? That's silly. It can be any set. So there are, if I want to say that I have, so if I have some set A, then to have arity A means I have A many arguments. So here's the general idea. Arity can be just any set. So if you want infinitely many arguments, you will put an infinite set here. Which one? Well, I don't care, the one that suits you. So as far as mathematicians are concerned, there isn't a lot of difference between putting here the natural numbers or pairs of natural numbers. Those all have the same cardinality, but when you're a computer scientist, you do care about whether your set is strings or lists or trees, even though they all have the same cardinality, right? You're not going to, so that's why I want this fidelity here. I want to allow this. And also, I am avoiding a whole lot of set theoretic complications by not using cardinal numbers. So arities are going to be sets. That's our first idea. So under this new view, when I have a signature, what will a signature be? So this is temporary definition, because we're not done yet. We need to add parameters. A signature would then be like this. A signature is a bunch of operations with arities. And I think of this as symbols, although they really can be anything. And these are just sets. And then when we give an interpretation of op I, what we're going to do is, well, we'll just replace this ni with the ai. So it'll be I to ai goes to carrier like that. So here it was obvious that I'm getting ni arguments, and here I'll have ai arguments. But these arguments, while here they're given to me as a tuple, here they're given to me as a function. Yes? They're given as a function. So now we need reasonable notation. So somebody might suggest, well, how are you going to write down terms when you have this? Because now the terms are becoming weird. Here, when we had terms, and these were expressions, it was clear that we can form expressions. But suppose this ai here is the power set of the real numbers. What does it mean to have a term? Well, it means to have a well-founded tree. So we're going to have to expand our idea of what syntax means, because I allow many arguments. Therefore, when I write down expressions, these will be infinite expressions, so to speak. So then the question is, how do I write them down? So you would say something like, okay, if I apply op I need to apply it to something. And then people will like say, oh, these are infinite tuples. So I have TA for every A in A, I, something like this. No, 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 no. We are programmers. What is this? It's a function, yes? So let it be a function. So it's just going to be op I applied to some function, which for purposes to be discovered later, I will call kappa, okay? This kappa is a function, so I'll just do it like that. So when I write my syntax, I will start using notation which is appropriate to functions, which is lambda calculus. So I wouldn't do this. It's much more likely that I will write something like this. I'll just write, I will start using lambdas. So this is a change that's going to happen. We're going to do this. We're going to start using general arities. And then, because I have a general arity here, my idea of syntax expands. These are arbitrary sets. And then I can write down functions like that. Yes?
So when an argument was just a term, I mean, an instance of a term is a function.
Yes?
So it's essentially kind of the same thing. I mean, we already...
I'm not doing much.
Okay, yeah. So the idea of a parameter is just a term which is specifically also...
I have not come to parameters yet. That's the next step.
Okay.
Right now, I'm just explaining that I want to allow general arities. I have not general...
Any set that doesn't have to be a set of numbers.
Doesn't any set.
Right. But I mean, isn't that just it's still sort of like the cardinality of that set expresses the arity of the question.
Yeah, if you insist on cardinalities, then I'll tell you to look at the cardinality of the set.
I see.
But we won't have any use for the cardinalities, so we can just forget them. They will be irrelevant.
Okay.
Yes. So then the next thing are parameters. So to motivate parameters, and then I'll put them both together and I'll write down the official definition. So for parameters, let's do a little bit of algebra. Let's look at an example of modules. Okay, so what's a module? Anybody know?
Which kind of module?
Okay, the one you will find in algebra. Something about rings. Okay, so let's do another one that will serve the purpose. Vector space. How about that? Better? Vector space is a special kind of module. So what is the algebraic structure of a vector space? Well, you have a vector space V, and then what are the operations? You can add vectors, so you can have V plus W, so there is addition. And then there is the zero vector, yes, that's important. And then there is the opposite vector, and these have some equations which give you the abelian group. But we're not done yet. There is one more operation, which is scalar multiplication, right? So there is also L times V, where L, let's say we have a vector space over the reals, okay? So V would be a scalar, lambda. Let me not use lambda. I know that books on linear algebra like lambda, but lambda. So S for scalar, and then V is a vector. And so you stare at this and you say, is this an algebraic theory? And then there are a bunch of equations. After this come equations, lots of equations. But they are just equations. So it looks like an algebraic theory, but it isn't. Because this operation here is problematic. What is this operation? This operation is you take a real and a vector, and you get a vector. Yep. So it's not of this form. It's not of this form, because it's got this real number sitting here. And so this is an example of an operation which is, so if I ask you, is it binary? What is it? The answer is, It's a unary operation because it takes one vector and gives one vector, but it also has a parameter. So that's one way of handling vector spaces algebraically. There are other ways, and if you read my notes, I list 3 ways of doing this. Yes? But the one that I will want is, sometimes I have an operation which takes some extra gadget here. So otherwise it looks like an algebraic operation, but it takes an extra parameter. And so I want to allow that. Yes?
Could we add one operation for each different value of scalar? And,
Yes. Yes, we could. So one of possible solutions is for each scalar, you introduce a new operation which is multiplying by that scalar.
Yeah.
So that would then give me lots and lots of operations. That's one solution. Yeah, it'll be lots of operations. But I'm going to use a different one where I have a single operation, but it gets the scalar as an extra parameter, because that's what I need later on. It works better. And when you read the notes, you will see the difference between these 2 approaches comes up even in computational effects. It's like the difference between having many states, like having many instances of the computational effect state, versus, that would be what you suggested, versus having a single computational effect state, but it has locations. And then you can look at locations. And the locations would be like the scalars. So now I want to allow parameters. So some operations don't have any parameters, and others have parameters, and that's annoying. I want all operations to look the same. So when I have an operation that doesn't have a parameter, what can I do? Can I introduce an artificial parameter? Yes, I can, but it has to range over what set? 1, the unit, right? If I say there is only one possible value for the parameter, then I don't have to mention it. So this operation here would be like this, but say addition, which is v cross v to v, it's a binary operation. And since I insist on a parameter, I will put a parameter in like that. And now I don't have a good way of writing this down, but we'll have to take care of that. So let's do that. So let's combine these 2. And then explain what so how exactly do people write on this one? Okay. Where do I want to write that down? Say again? I haven't quite succeeded, have I? Now comes my punishment. Oh. So let's go over this again. Now we have to go over this again, yes? All of this and see what's changed. So here are the new definitions. Signature, sigma, now is going to be given by a bunch of operations, and each operation is going to have an associated parameter set and an arity. So the general case will be, just as a reminder what it is that I want, it'll be something like this. It will have an additional parameter set, and then it'll have an arity like that. This is the parameter. It takes this many arguments, and it takes an additional parameter from P. So I need a notation for that, and I will invent a notation that will come in handy later. So this is going to be, I'll write them like this. It's a bunch of operations, and each one takes a parameter. And so now you might expect something like a comma, but I'll write a wiggly arrow that doesn't mean anything. Like that. It'll be clear once we start doing programming why I'm writing it like that. This wiggly arrow means this is just notation for the moment. This is not a function from PI to AI or anything like that. It's just it's my way of writing things. It'll start to make sense later. So this is a symbol. This is a set. It's called a parameter set. And this is a set, and it's called arity. Now, terms. Now, when I have terms, now something happens. Because I can have infinitely many arguments, I have to allow arbitrary number of variables as well in order for theory to work out. So here, I'm going to have an arbitrary set of variables. But then my terms will look exactly like trees used to look yesterday, right? Yesterday we were building trees. Actually, terms are a special case of trees. So I'm just going to have trees, and I might call them trees or terms, it doesn't matter. So instead of terms, I'm going to have trees. So what are the trees? Return x is a tree for every x in x. So think of x as the set of variables. If you want to have the syntactic view of things, you think of this as the set of variables that can show up. And so return x, and I haven't really explained why I'm calling them return, but I need a tag. And then let's try the other one. So the other one is going to be op I, a parameter kappa is in 3 sigma x 4. And now tell me what's going on. P has to come from where? P will be the parameter, so it has to come from pi. And kappa, what's up with kappa? Kappa is what? It's a function because op I wants ai many arguments. To give ai many arguments, I need to give ai into, for each element here, I have to give an argument. But these arguments are supposed to be terms I'm building, or trees. These are the subtrees. So this is a function which will give me ai many subtrees. So that means that it maps into 3 sigma x. And you read this as an inductive definition. And you can have fun writing this down in calc or agda. It works. So those are trees, that's the terms. Okay, then equations, well, we just give 2 trees. Okay, so equation, well, now you give a set, and then you give L equals R, where LR are just trees. And this will all look exactly like, as long as this x here is finite, it'll actually look like syntax. But even if it's not finite, who cares? Now, a theory doesn't change. A theory is a signature and some set of equations. Okay, how about interpretation and model? Let's write that down, just so we can practice these kappas here. So an interpretation, what do you get? Well, again, you give a carrier set, which I write like this, and then for each op I, and now I can start using my notation like this, give a map op I, which goes from where to where? Well, that's the idea there. So from pi cross I to ai to I. So an operation symbol gets mapped to an operation, which is a map. It takes an extra parameter, then it takes a many arguments, and it produces a result. What's a model? Oh, and then we can extend this to to interpretation of trees / terms. So let's write it down. Okay? So if I have a tree then it will be interpreted as what? So now I have to generalize what I had before. So think of it this way. Earlier I had some, so when you have, let's remember. So the interpretation of a term like that was x1, xk, t, let's put this k here. It was I to the k to I. So now I'm replacing this with x, so a set of variables, and so this k will just become this set, kx here. And since we're computer scientists, what is going on? Well, this thing here is a function that maps variables to their values. It's the runtime environment. Yes. Okay, it just maps variables to. So how does this work? Well, if I have a variable x, so it's return xi. Do you have your favorite letter for runtime environment? Gamma? Sure, why not? But the little gamma, not the capital gamma. Capital gamma is a typing context, which is different. It's the type of a runtime environment. So it maps little gamma to gamma at x. And if I have op I p kappa, we are going to start reaping benefits of lambda calculus right now, because it'll start, so we can actually write down things. So what is this? Okay, so this is supposed to give me an element of I. So I have to come up with an element of I. How will I come up with an element of I? I will use I. Op I wants a parameter, and it wants a many arguments. Do I have a parameter? Sure. Here. Do I have k many arguments? Well, ai many arguments. Well, kappa almost does it. Kappa maps into trees, but recursively I can map trees into the model. So this is going to be the interpretation. So I want lambda a in ai, kappa a, I, gamma. So what happened here? For each position, for each index of an argument, right? I want the 8th argument. What is the 8th argument? Well, I look at the 8th subtree and I interpret it. And I get the 8th argument. Now, how about model? Well, now model will be the same as before. Model is an interpretation which validates equations. So you take your equation, you interpret left and right hand side, they have to give you the same thing. So model as before. An interpretation which satisfies equations. How about free model? Okay, so let's do the free model. And after that, we do examples. Am I right? Yes. So, what is the free model of a theory generated by some set X? So remember yesterday's idea was you put in only as much as you need to, both in terms of elements and equations. You only create those elements that you must, and you only enforce those equations that you must. So that means we're going to have trees quotiented by something. So it's going to be trees quotiented by, and then enforcing equations of the theory. I'm not going to drag you through this. In the notes, I wrote down very explicitly what this means, and you can read. And I'm not going to drag you through it right now because it's not that important. We will see some examples, and when you have the examples, we will be able to deal with the particular equations. And right now I don't have to, because the definition is going to be, oh, what does it mean to be a congruence? What does it mean to turn an equation into something that is, okay? So read it in the notes. I don't want to do it right now. So I want to move over to something that is much more interesting. And the interesting bit is, so this is essentially now setting us up. This is the amount of math that I need so that I can speak about 5 computational effects as algebraic operations. Let's just take kind of an naive view here, okay? So computational effects, what are computational effects? They're the stuff that's not in the lambda calculus. So printing, reading, stateful memory, exceptions, non-deterministic choice, strange stuff like delimited continuations. So those are generally effects. They are the things which distinguish programs from mathematical functions. It's kind of an open-ended concept, and it's difficult to pin down because people can come up with new ideas of what computational effects are. You know, somebody builds new hardware, oh my God, now we have quantum computational effects. So it really changes with time. But there are lots of examples of them. And how are they manifested in a program when you write a program? When you write a program, if you want, let's take a particular example. Let's take the example of printing and reading. You print to standard output and you read from standard input. Well, you write print and then stuff gets printed. And if you want to read something, you say read. And then the whole program is waiting for the user to type something, and the user types something, and then the read tells you what got read, and then you can go on. Similar for reading from disk, or actually modifying memory is like that. You can move something from memory, and then the processor has to wait forever for memory to produce the answer, or you can write something to memory. And so they all look like you issue an instruction, and the instruction performs the effect. Well, let's not call it instruction, let's call it operation. So we can think of creating or causing or triggering effects by running operations in a program. So naively, then we can distinguish computations. Let me say computations as in the things that happen when we're running a program. And, well, they can be pure or they can be effectful. If they're pure, that means they're not actually doing anything. They're not causing any kind of computational effect. And the canonical example of such a thing, we can write it like this: return V. Because if it's not doing anything, then I can just reduce it to its result whenever I like, if it's not doing anything. Because if I have a piece of code that is not going to trigger any computational effects, it doesn't matter whether I calculate it now or later or once or twice. It's going to be the same. Mind you, that non-termination is a computational effect. So when I say that it's pure, that also means that it's terminating. It terminates. Because if it's non-terminating, then that is a computational effect. In fact, non-termination is the most interesting computational effect of them all. But I am going to ignore non-termination until further notice. I'm only talking about programs that terminate. Then in that case, it's like that, right? Yes?
Just before you go on from combination, what about productivity?
Productivity in what sense?
But it always, so it continues forever, but it always returns a result as the next step.
So in our case, productivity would be something like a program that goes on forever and keeps printing, for instance. Yes? And then you see, yeah, it's doing something. I'm ignoring that kind of program for the time being as well. So my programs right now are going to be always terminating because I can tell you why. Because my trees are well-founded. Okay? So that would be a pure computation, and then an effectful computation would look like this. You would say, we run an operation. But when we run an operation, when we trigger an operation, we have to give it, well, in general, let's see what happens. In general, when you run an operation, you don't just run an operation, you give it an argument. For instance, when you print, you tell it what it is that it needs to print. That's the parameter. So an operation takes a parameter. The location of the memory to read from, the string to be printed. Some operations don't take any parameters, but we know the trick. When they don't take the parameter is the unit. So they always take parameters. And then what happens? Well, operations in general also return results. When I read from memory, I get a result. And then the program takes that result and does something with it. It continues when it runs. It cannot run until it gets the result. So it gets suspended, the operating system starts doing stuff, kernel mode, blah, 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 read, come back, come back, come back, come back. Here, there's the result, go on, yes? So there is also going to be a result, and this result needs to be fed into the rest of the computation. So here sits, so this is the parameter. This is the rest of computation awaiting the result of the operation. Like waiting for the string to come, waiting for the contents of the memory. And once the contents of the memory becomes available, there has to be a mechanism that is going to restart kappa by feeding it the result. So kappa is going to be really like a function that is awaiting the result of the operation. So with this notation, let's just practice notation here. Yeah, sure. I designate you as my official board manager. No? Wrong? I see. I have a good board manager. Okay, so example. Let's do this. There are venerable programming languages that have that, okay? So what is that? That is, here's a pointer, and it's increase, what do I want to do? Increase its value. No, and return the previous result. Okay, so how would we write this? And suppose I'm just going to do this a little hand wavy now, and then we'll do it exactly. But so what would be the basic operations? The basic operations would be to look up a memory location and to update a memory location. So you'd write something like this. How do you do this? You'd say, well, first of all, look up the memory location L. That's the first thing I will do. And then it's going to come, and this will be the contents. I'm saying, okay, then you're going to get something. It'll be some sort of X, which is whatever is at that memory location. What do you want to do with that? Well, after that, I want to update the memory location. Which one? I want to update L with what value? With value X plus 1. And then this operation, update, is going to return a result. But this result will be trivial. It'll be the unit, because when you update a memory location, nothing comes back. You're updating. So the unit comes back. I can ignore it. So I'll write an underline here. And then I want to do what? Well, then I want to return X. And if I had plus plus L, then I would put X plus 1 here. Yes? And I just feel like we really need to do this one. Yes. There's an important point here about the order of things. This one, you can't see anything here. You can see it here. First we look up, then we update. Yes? The outer operation happens first. Then, once its result is known, we activate the continuation, and the rest happens. So you have to read this from outside in, because this is always a question when people think about this, is, oh, shouldn't it happen from inside out? No, it happens from outside in. Yes?
The parentheses are unbalanced, and it's actually relevant.
Yes, which parenthesis? Here. Yes, okay. So lambda always goes as far as it can. So first let me balance the parentheses. Okay, and now the question is, would you like any extra parentheses to clarify the matters? You're happy?
I was thinking of
Yeah.
the commas, the sequentiation operator. And I was wondering
Oh.
if you need a parenthesis
Yeah.
after the
Yeah.
comma, and then
Yeah.
you do the other
No.
thing.
The comma is there just to, the comma is there just to tell, just because the operation takes a parameter and a continuation. Yeah. Okay? Now let's make this, let's see if we can now look at some examples of these. Yes?
So where is the runtime environment coming in?
There is no runtime environment right now because these programs don't contain free variables, or it's empty. So these would happen, when these happen, this X here would be empty because, well, let's be careful. What I called runtime environment there, I will actually end up using it in a different way. It's not going to be the runtime environment, okay? So there won't be any explicit runtime environment in what I'm doing.
Sorry.
Yes?
I know you too.
Yeah, no, we are at a very important point where you need to understand what's going on.
Computer science,
Yeah,
I don't know,
yeah.
I'm trying to deal my intuition. So you're defining the operation lookup as it's a morphic structure that you have to pull the tree from the hang that because you're dealing with the memory. It's an update operation. That belongs in another level of discourse, right? It's part of our...
Oh, where will the actual memory come from?
The word update, right?
Yeah. Yeah, oh, no, this is...
You're thinking about
Oh,
memory.
okay.
Update is not an operation, like, for instance.
Oh, it is.
Something
Update. So, well, actually, let's be precise. This is an operation symbol. I'm just practicing how to write down source code, but I'm not explaining what this source code means, and I'm not really defining how it's supposed to run.
I'm not to explain it now, but I want to know if update is in the same word as BOPs.
Yes. 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 So the operations are. Yeah. Okay.
So update takes two arguments, but one argument is appear.
Ah, yes, yes, of course. So let's be careful here. So this is a parameter. So let's write the signatures. That's why it helps to write the signatures. So what would be the signature for lookup? The signature for lookup would be, it takes a location and it gives me back whatever is written in the memory state. And what does update do? An update will take a location and the new state, and it gives me unit as a result. What does print do? Oh, not a function. It goes from string to unit. Yeah? And when you see this, then you can read off what's going on. Because update has, because here I have L cross S, this thing here is an element of L cross S. And because here I have 1, this thing here, kappa, is going to go from 1 to something. Let's work out an example to see that we can actually describe what is going on using algebraic theories. So I'm going to do state again, but now I'm going to do a single state. State holding elements of a given set S. So I want to have an effectful computation, and the possible states are the elements of S. So for instance, in my iPhone, S would be the set of all possible configurations of RAM. That would be my state. It's a big set, but it's only finite. So what would be the operations? Well, the operations would be something like lookup and update, but let me write put and get just because they're easier to write. So I'll write them put and get also to distinguish them between this other kind where you have locations, because now I don't have any locations. It's like having a single location. I just have state, and I can say, what is the state? Or change the state. So signature has two operations. Let me call them put and get. What does put do? It takes the new state and then doesn't return it. Then what does get do? Doesn't take anything and returns S state. How about equations? We should try to write down some equations here. Yes, and there are 4 equations, I think. Let's see if we can figure them out. Once I write the first one, you will then be able to suggest some others. So if I do this, get, so I say get the state, I need to feed it the unit. And then after that, I get the state, and it's X. And then I say get me the state again, read again. So I read the state, and it's X. I read the state, and it's Y. And then I do something with it. So here I have kappa, which depends on X and Y. So then something happens afterwards. Is this equal to something? It seems unnecessary to read the state twice in a row. If it's state. This is not standard input. This is state. Because it's state, it should be the same if I read it twice. So this should be the same as reading the state once, and I get it out, let me call it Z here, and then I just do kappa ZZ. So this equation is telling me what happens if I read the state twice in a row. Why will there be 4 equations? Because there are 4 ways of combining 2 operations, and for each one I can say something. So I'll write down the left-hand side, and you'll tell me what the right-hand side is. So let me do get put. Let me do put get. Actually, this one, get lambda x put x kappa. X. Apparently, I can go wrong. That's better if I don't. Get lambda s put s. Yeah, this is a good one, and I don't actually need this x here. That's wrong, because kappa expects the result of put, which is unit. So this is going to be unit to something. So what happens if I read the state and then I write it right back in? I could skip these 2 operations. So this should be the same as kappa applied to the unit. Okay, let's have another one. First, I put.
I'm sorry, so kappa's closed.
Kappa is, let's see. So these are terms. These are terms. So yeah, so kappa is going to be a function from unit to terms. Right. So yes, so if I wanted to allow kappa to depend on x, I would have to explicitly parameterize it, but I'm not. There is a subtle question about what exactly is this kappa. Intuitively, you think of it as an arbitrary computation that happens later. But in the notes, I was careful to explain exactly what you need to do to understand what kappa is. Kappa, it has to be the generic continuation. So I'll offload that to the notes, or you can ask me later. So how about this one? We put something into the state, like we set it to little s, and then we read it. And we read it, and we say, oh, look, it's x. And then we do something with it. So I can just write it like that. So first we set the state to little s, then we read it, and then we're going to feed that into kappa. It's not kappa s. Because if you say that it's kappa s, you forgot to update your state. Maybe beforehand the state wasn't s. You cannot just delete this put. You have to keep the put. But you don't have to read because you know what's in it. Right? You can get rid of the get, but not the put. So this is put s. And then here is lambda kappa. Okay? So here kappa will get the result of the reading, but I know what it is. Kappa s. And then there's one more, which is a double put. And that one's going to be easy, right? Put s, put t, kappa. What can we do here? We forget the first put, just the second put has to be there. So it's put t kappa. And so these are the equations governing state. And you have more examples in the notes. But one thing should be clear. It's algebraic. And so Gordon Plotkin and John Power noticed this, and they said, wow, a whole lot of algebraic effects are of this form. We can express the behavior of computational effects using algebraic theories. And so that's good. Well, some of them they couldn't, but a lot of them they could. And those that can be so described are called algebraic effects. So an algebraic effect is a computational effect that can be described using this kind of formalism. Yes?
Can you please
continuations is one of them. Another one that they didn't know how to do were exception handlers. So maybe we can have a look at this example, just because it will be come in handler example. Let's do exceptions. So let's do the simplest kind of exception. The simplest kind of exception is when you just have an exception that you raise without any data and it just aborts the program immediately. So I will call it abort or exit, but I'll call it abort. So you would say abort is an exception. Okay, so let's think about it. I'm saying it doesn't take any parameters, so unit here. But the interesting question is, when you have an exception, how many arguments does the continuation expect? Well, when you have an exception, does anything happen later? No, because when you run an exception, when an exception happens, you're not going to go back and continue the computation. That's the whole point of exception, is that you're not going to do that. So we need to write that down somehow. How do we write that down? We say that the continuation expects 0 arguments here. Because that is going to mean that in my model, when I have a model, this will say 1 cross m to the 0 to m. But m to the 0 is 1, which means the continuation, formally the continuation is there, but it's stupid, because there is no way that you can restart the continuation. This is a continuation, and you can restart it by giving it, okay, so sorry, this should be empty set. By giving it, you can restart the continuation if you give it an element of the empty set. Good luck. So it's not restartable. It's a non-resumable, because, well, the empty set is empty. So there's nothing you could possibly pass to it so that it will continue. There are no equations. A lot of effects have no equations. Standard input and output, no equations. Now, one thing that puzzled people for a while was what's going on with exception handlers, because we don't have just exceptions, we can also catch them and then we handle them. And that did not fit the algebraic picture. Handle is not an algebraic operation. However you try to do it, you fail. But there is a different concept that arose out of that, which we're going to consider, which is a very powerful concept of a handler, a general handler. So by trying to fit exception handlers into this framework, it was Gordon Plotkin and Mattia Pretnar who invented handlers, and we're going to get to that. Okay, now, if we look at this, all this stuff here, I said earlier, well, I'm giving you just operation symbols. I'm not actually telling you how to run these things. That's true. That's a different lecture. But we should ask the following. Once I have a description, this is a theory now. What I have here is a theory. Well, there should be some models. Do we know that there are models? Yes, we know there are models. There's the trivial model, always. But there is also the free model, and there are probably very many models. After all, you can take the product of 2 free models, and then you'll get something. So there are lots of models of any given theory. Which model is the one that we really want? Which of the models? So models are mathematical structures. Presumably, one of them corresponds to the thing that's really going on, the thing that we would like to have. And so here, you have to think the following way. Are there any other equations that you would like to write down here? Or are you happy with these? If you are happy with these, if these are all the equations that you need in order to properly describe the computational effect known as state, if these are all of them, then it will follow that the free model is the one you want. Because the free model is the one that will make these equations true and no others, except by necessity. Therefore, it has to be the right one. If it isn't the right one, you either put down too many equations or you forgot some. But if you got it right, that will be the model. Yes? So the free model, so this is worth writing down somewhere. If my board manager will allow me to. Oh, I can't move this one. Okay, so. The free model free t, and let me call it v here now instead of x so that people don't think these are variables, is actually the one, let's see, the free model is for us the set of computations with effects described by theory T and returning values from set S, so from set V. So again, I can use these operations. So these are the effects, and these are the return values. Because all my computations are finite. They all terminate. So every operation that I have, every computation that I have, when I run it, it's going to trigger some operations, these ones. But eventually, when it terminates, it has to give me a result. It'll end up being a return of something, and then it will be a return of some element from here. Okay? So if I say something like free state int, that would be so the elements of this ought to correspond to computations, which can use state from this element S, some fixed set S here, that use state, and then they return integers. In the notes, I recommend that you read, I actually go through this, and I calculate free state of V, and I show that it actually corresponds to, so we do it like this, that this one, so in general, if you have a V here, that this one is actually isomorphic to, and now all the Haskell programmers, hold your breath, S to S cross V. And that is what you want, right? If you're a Haskell programmer. How do you do the state monad? That's the beginning of the state monad. So that means, by the way, I'm going on until what time? Noon, okay. So that's the state monad. Let's just see how does this work. How do you calculate this? Let's spend 5 minutes thinking about this. So this thing here is defined as trees. There must be some board that I don't need. What does this one do? Oh, this is old stuff. So I have here where state is the my board manager Something's wrong. It's this theory, yes, this theory here. So, well, this one is defined to be trees, state, V, modulo, state thingy. And so what happens is that we have lots of trees, and there's an equivalence relation on them. And so now what we need to do is we need to figure out what do these equivalence classes look like. And let's do that. So you stare at this and you say, okay, in my equivalence class there is a tree. Each tree is either it's a return or a get or a put. If it's a return, that's a simple case, it's a return. If it is a get, then it has some subtrees, and if it's a put, it has exactly one subtree because put returns the unit. But there's a bunch of trees and some of them are equivalent. And now I'd like to see how do I manage these equivalence classes. It's in the notes, but here, let me give you the idea. Will you ever need to consider a tree that has two consecutive gets? You never need to have two consecutive gets. So if you have a tree that has two consecutive gets, you can reduce the number of gets. Will you ever need a tree which has a get then immediately followed by a put like that? You can get rid of that. And can you get I think this one might be wrong. So, and then you never need to have a put followed by a get, and you never need to have two puts. And so what you do is you see that every operation, every tree, whatever you're doing with your state, you can always get rid of these combinations of gets and puts and everything. You can get rid of them, and it'll always take the form, I read the state, I set the state, I return the result. See, whenever you have a computation that is doing gets and puts, you will be able to bring it to the form, first I read the state, then I set the state to its final value, and I return the result. Because if you did any kind of intermediate reads and writes, you can fold all of that into a single get followed by a put. Right? And that's exactly what these equations are telling you, that you can do that. First, I read the state, then I set the state, and I return the result. And there you see your isomorphism. And now you can play this game over and over. And so now, because, Haskell, monads, you say, but this is a monad. Yes, but this is a monad as well. So the free models form a monad. I'm not going to explain that because I'm afraid I have to explain monads first. So it's in the notes. If you know what a monad is, please read it. If you don't know what a monad is, type monad into Google and pick a tutorial at random and spend 5 minutes reading it. But no more than 5 minutes or it will be harmful. But let me tell you what the story is. There is a general monad structure on the free models, and this monad structure will agree with the desired monad structure induced by the computational effects that you know and love. So there is the instances that we care about that appear in practice, they are of course known in terms of monads, and you will get exactly the monads that you know. So it all works out beautifully. So there's a monad structure there. Now, yes?
The free models of this theory of effects?
So,
or all free models of every theory?
Input, output, exceptions, state, non-determinism, at least these were verified already by Plotkin and Powers that they give you what you want. Yes. And once you see that they give you what you want, you start believing that if there is one that doesn't, then it's the other side's fault, right? You almost like, but yeah, they work out. Yeah. So that's good. Okay, let's see, we have 10 minutes. Maybe one thing to do is improve on our notation, because frankly, Nobody wants to write programs like this, let's be honest, okay? So this kind of writing programs is awful because you need to write explicit continuations. It's explicit continuation passing style, and that's not good for humans. And also mathematicians complain when you write these things. But let's make at least programmers happy by improving the syntax. Do you have a suggestion where I should write that? This one here? Just this one? That one? Okay. Oh, look, it's empty. Okay. So, better notation. That's number 6-ish. Generic operations. And sequencing. And so I will introduce new notation. I will not do anything fancy. This is just notation. So first of all, if I have an operation, then I define the generic operation. Corresponding to this operation to be op, and I will put a line somewhere, like here, to distinguish it. Op of P, by definition, means op of P, and the continuation is just return. So an operation always needs to, you run the operation and afterwards you do something. What's the simplest thing you could do? The simplest thing you could do is you just return the result that you got. Yes? So this operation will, like for instance, if this is read, you get a string, all you do is you return the string. Here's the string I got. These are the operations that actually appear in programming languages. That's what they are. When you write read in Python, it is that. You say read, and then I think you even have to put the unit there, right? And then a string comes out. And the other thing is called sequencing. There are some competing notations for this. Let's take the middle ground. I'll do it like this. Do x. It's possible to do this wrong. And so here you have some, because I'm doing just, this is a tree or an expression in like this. I want to have a notation for this, okay? And I think I can pull it off. So I have to explain what this is. So first, here's the intuitive explanation. What this means is, so let me write, it will be slightly easier if I write t of x here, like that, okay? So I want to do the following. I first perform computation P1. Computation does its effects, whatever they are. There can be many operations happening here. And eventually it gives me a result. And that result goes into X. And I feed it into this other computation, and I do that computation. It's a lot like Haskell. Let's just see what it would be. Like in Haskell, it's that, except that what's it written like? Do x t1 t2. And in ML, it's let x be t1 and t2. And in C, no, it's not. It's not, right? Let's be careful. This is in C. It's not this. This is something else. This is an effectful operation which is changing state. This is more like put something, blah, blah, blah. Yeah? It's a put because it's going to change state. So we want that. And this notation works for the free, to explain what it is for the free model. And I will do that and finish with that. And the point is, so actually let me write it down like this. I'm going to define for you what do does by recursion. And then you can read the notes to see how that has to do, what that has to do with the free model. So the two cases are, we define do like this. Do x. So what are the two possibilities for this T1? The two possibilities are that this is either a return or it's an operation. Okay, so if it's a return, then this is going to be T2 of V, because I just get my V and I feed it in. What if it is an operation? Do x, and this is an operation with some parameter P, and let's use the old notation still, kappa in T2 of x. It's like that. Well, what is the first thing that will happen when you run this? It's this operation. And when this operation happens, then after that, other things will happen. So the first thing that happens is this operation. And then afterwards, what will happen? Afterwards, this operation op is going to feed its result into x. And then, once the, sorry, I forgot the kappa. What? Where is it? It's this one. Actually, here it's like this. Y. Okay, so I run the operation op, and this operation op is going to produce some y, and it will feed it into kappa. Yes? And then stuff will go on, and eventually an x will come out. So what I need to do is, here I do x kappa y in T2 of x. So the first thing that happens, I'm counting on your computational intuition here, but if you read the notes, you will see how this works with free models. The first thing that happens is the op. So it's the op. This op produces a result and feeds it into kappa. We get the result, we feed it into kappa, kappa does its work, and whatever kappa returns goes into x, and then T2 continues. And so this is how you can define the do notation. And it's really a recursion on trees. Yep. And now the beautiful thing is that we can get rid of this old notation once and for all, because we have that op p kappa is the same thing as do, so let me write it like this, lambda x kappa x, like this. So this is going to be the same thing as do x, the generic op in kappa x. So let's think about this. So I introduced generic operations as this abbreviation. I introduced sequencing by recursion on the trees. And now I claim my old notation is expressible in the new notation, so I can also forget about the old notation. So let's see if this is really the case. We can just work it out. So what is this? So I'll leave it to you to work it out. So you plug in for op, this thing here, and then you are in this case, and you have to unfold this once, and you'll get the op, and then you will have here do x return, and then you can do it again. And so because of that, I can now use the new notation. So here we have a programming design point. Let me finish on that note. So this is typical. So behind the scenes, something's going on. That's the old notation. The old notation is when we know that operations have continuations, and we explicitly speak about these continuations. This is not what you want your programmer to see. I mean, you can if you're crazy, but then you're going to have a weird programming language. So maybe you shouldn't do that. You should always remember, programming languages are there because of humans. Machines don't need any programming languages. Programming languages are there for humans. It's the same like horse riding. The bridles are there for the human, not for the horse. The horse doesn't want the bridles. Okay, so keep that in mind. So we're designing for humans. So we're going to give them do and op. That's what we're going to do. We'll give them just the generic operations. They will never see an op without the overline. And so the programmer, to the programmer, op looks like what? Op looks like a function taking a parameter and returning a result, which is the arity. Which is why I use this notation. So when you have an operation in a real programming language, it looks like a function because it is actually the generic operation that you see, and it takes a parameter and returns the arity. And the continuation is whatever source code comes afterwards. That's the continuation. Okay, so let me finish here. So next time, we should be doing handlers. I'm hoping we can do handlers and models and code models, and we are going to discuss how do you turn this into a programming language. Like we'll actually write down operational semantics. You can write down, so I will ask you, could you suggest good operational semantics for do? But unfortunately, you will not have this on the board at the time, so you'll have to go back and quickly find this, okay? And they will say, how about these two transition rules? See, these are equations, but they have a definite direction. And we're going to use those directions to give operational semantics. Thank you.